Hello, everyone. Thank you for joining us in this session of our webinar series. My name is Roland, and today we are joined by Reese Fernandez of Tally and Tom Bell of ConcealFab. We'll be talking about PIM, what it is, the solutions available, and the need to achieve low PIM. But before we do, I'd like to introduce Reese Fernandez, Tally's 5G Applications Director. Reese, can you tell us a little bit about yourself, please?
Sure. So my name is Reese Fernandez. I'm the 5G Applications Director for Tally. What that consists of is about 16 years of dedicated service to the distribution world and wireless infrastructure. One of the main roles for the new generation of small cells that are coming out, and in my role, is to ensure that we have all of the proper product that helps satisfy all of the needs for the new technology, not only from the radio perspective, but also from the infrastructure and the hardware that's being put on there. And so today, we're joined with Mr. Tom Bell from ConcealFab to talk specifically about one of the low PIM cable support solutions that we're going to be providing for them as a distributor. So Tom Bell, welcome, and please introduce yourself.
All right, thanks, Reese. I appreciate that. My name is Tom Bell. I am the Executive Vice President of Product Line Development at ConcealFab. I've been involved in the PIM industry for more years than I care to mention, but I did work at both the major PIM test equipment manufacturers before joining ConcealFab and working on product solutions. So the presentation that I'm giving here today is titled Low PIM Cable Support Solutions, but we're also going to not only talk about the products themselves, but step back and discuss the changing RF environment at cell sites that is driving the need for these new low PIM solutions. But I'm going to start off with a walk down memory lane. And here in the picture is a picture of a site taken back in 2008. This is in the Los Angeles area. And, sites back in the day were relatively simple. Here in this particular site, there's only 2 bands deployed. It has PCS and AWS deployed. There's 2 antennas per sector and 2 tower-mounted amplifiers per sector. All the radio equipment is at ground level. And at the top of the tower, the only thing we have is a small amount of coax, we have RET cables, and we have grounding cables. The support requirements for those cables were mostly mechanical. So we had to be concerned about supporting the weight, including both an ice load to keep the cables from slipping within the support. The supports also had to prevent the cable from moving during wind to provide strain relief for the RF connectors. And they had to be designed to withstand harsh tower top environments. There's really only one RF requirement associated with cable supports, and that is that the support had to be designed such that it was not going to crush or deform the cable, which can cause high RF reflections. The solutions that were out there at the time were almost entirely stainless steel. We had stainless steel round member adapters, which is code name for hose clamps. We had stainless steel standoff brackets and custom stainless steel clips to grip the cable. There were also a lot of stainless steel angle adapters and stainless steel threaded rods. So a lot of stainless steel here, and it was fit for purpose. It met those criteria that we just described. But now let's fast forward a decade and look at the picture of that exact same site in Los Angeles taken in December of 2019. And you can see things are significantly more complex. We now have many bands deployed at this site. We have the original PCS and AWS that were there in 2008. We now have 700 megahertz, 600 megahertz, and probably by this time, there's probably 2,500 megahertz deployed on that site as well. There are multiple multi-band antennas per sector. We have antennas with integrated radios as well as remote radio heads deployed. There is a ton more coax deployed at this site. We still have RET cables, ground cables, but now we have the addition of fiber running to the radios as well as power. So these changing requirements caused by all these new bands being deployed on this sector has now changed the mounting requirements for cables at that site. the original requirements are all still there with regard to the mechanical support and the one RF requirement. But we now have two additional requirements. One is just sheerly because of the higher count in cables, each support needs to be able to support more cables per attachment point. And in addition, we now have to be concerned about the PIM performance of those mounts. And let's step back a minute and talk about, well, why is that? To start with, let's talk about what is PIM. Well, PIM, or passive intermodulation, is interference. It is the generation of new frequencies that are created by the transmit signals at a site when they encounter anything nonlinear in the RF path. When high magnitude PIM is generated that falls in the operator's uplink, it's going to elevate the noise floor, which results in dropped calls, reduced coverage, access failures, and slower data rates. But you might say, well, what's happened? Why all of a sudden is the PIM magnitude getting higher? And it turns out it's because of these new bands that we're deploying. Traditionally, we were only generating high order magnitude products in the uplink, and now these new frequency bands are able to generate low order intermodulation products, such as IM3, that falls in the operator's uplink. And that's a big deal because IM3 is significantly higher magnitude than those traditional high order products. So for example, if it was seventh order product that was falling in your uplink previously, when you have IM3, it's now 3,000 times or more than 3,000 times higher in magnitude. And if you traditionally had IM9 falling in your uplink, you're now looking at a signal that's more than 100,000 times higher in magnitude. So what's happening is PIM sources that were previously below the noise floor and not impacting service can be now as much as 50 dB higher in magnitude, which certainly can and will impact service. So let's look at a couple examples of new frequency combinations that are happening that are causing these problems. First, let's look at the AT&T deployment of band 14. Band 14 is the new 700 megahertz spectrum that ththey're using to deploy the FirstNet network. They traditionally had band 17, which was their low 700 low band that was used for the original deployment of LTE. That original band 17 spectrum, because the transmit frequencies were relatively close together and the band where you're receiving was relatively far apart, you could only generate a seventh order IM product from those transmit tones that would fall in their uplink. But as soon as I add band 14 to the mix, now the transmit frequencies can be much further apart. And when you spread the transmit frequencies apart, the intermodulation frequencies spread apart as well. And so now, the PIM sources didn't change, but all of a sudden now the products that are able to be created by those PIM sources are now these low third order intermodulation products. And they're able to be generated in both the band 17 uplink as well as the band 14 uplink. Looking also at the new 600 megahertz spectrum, which is being deployed across the country by multiple operators, how bad that is, or the intermodulation products that are generated from that spectrum depend on how much spectrum you're deploying. So here again, the further apart you can have transmit frequencies, the wider the distribution of the intermodulation products. So if you're in a market that only has 10 megahertz of 600 megahertz, you're going to have a ninth order product falling in band, which really isn't that bad. But if I'm in the unlucky markets that have 25 megahertz of 600 megahertz, you're looking at a third order intermodulation product. Most of the country, if I look at T-Mobile's deployment, they got typically 20 megahertz per market, which means that they're still looking at a fifth order intermodulation product caused by that 600 megahertz transmit falling into their own 600 megahertz uplink. Another concern with 600 megahertz is its impact on the PCS spectrum. 600 megahertz by itself can generate a third order intermodulation product that falls into the PCS uplink. The math that's generating that is not the traditional 2 times F1 minus F2. Instead, we replace the minus sign with a plus sign, and that's the frequencies where these products are occurring. A simpler way of thinking about this is that 3 times 600 equals 1800, and 1800 is where the uplink is for PCS. The chart here shows that for every 5 megahertz of 600 megahertz spectrum I have, I'm going to create a corresponding 15 megahertz of IM3. It falls in different sections of the PCS uplink. And if I'm that typical T-Mobile market that has 20 megahertz and they're typically using the B, C, D, and E blocks, they're generating a 60 megahertz wide IM3 product that covers almost the entire PCS uplink. All right, so those are just a few of the frequency combinations that are out there that are causing this new problem. And with the new auctions that are happening now for the CBRS band and the auctions that are going to happen for C-band, we're going to find a lot more frequency combinations of concerns coming along here soon. Now, the traditional supports that are out there have evolved over time and are able to meet the requirement of being able to support more cables per connection point. So we have stainless steel 3-way adapter brackets that can be deployed, as well as now it's very common to see stackable snap-in hangers to be able to get more cable support at each connection point. And if you're in a market that's using cable support blocks, those can be deployed on threaded rods, and multiple cable support blocks can be secured at a single mounting point on that rod. The problem is that these traditional supports are not low passive intermodulation. There's 2 problems here. One is caused by galvanic mismatches, and the other is caused by loose metal-to-metal contact at the supports. On the galvanic mismatch side, stainless steel and galvanized steel are at opposite ends of the galvanic series. And what this means is that wherever galvanized steel is touching stainless steel, it's acting like a battery and creating this white powdery corrosion at the mating interface. Now, the corrosion is not a structural concern because it's self-limiting. Once the powder is created, it stops eating away at the metal. But that powdery corrosion that's been created is highly nonlinear and is a very high magnitude PIM source. From the standpoint of the loose metal contacts, metal snap-ins are great from an ease of installation standpoint, but by definition, they're not bolted connections with high contact pressure. And so therefore they inherently have loose contacts. And then just due to the sheer number of connection points, we end up with the tails of the threaded of the hose clamps able to touch other things, as well as adjacent brackets able to touch each other. So this traditional method that we've used for supporting cables mechanically is fantastic, but from a PIM perspective, it just doesn't live up to the new requirements. Now you might say, well, wait a minute, we're not putting these things in front of the antenna. They're going to be placed behind the antenna or maybe even beside the antenna. Why do we care? And it turns out that in the area very close to an antenna, you have a very high level of currents. And this area is referred to as the reactive near field. There's the equation for calculating it if you're so inclined. But the area we find from experience in the field is that the biggest area of concern behind the antenna, above the antenna, or below the antenna is a region within one wavelength of that antenna. And here, anything you place in that area is being subjected to high currents, and so therefore is able to generate high magnitudes of PIM back into the system. The chart here shows how large a wavelength is versus frequency. So at the higher frequency ranges, such as the PCS band, you can see that a wavelength is only 6 inches. But when I get to 600 megahertz, a wavelength is over 18 inches. And there is a lot of things mounted at cell sites within 18 inches of that antenna. Now, when we take into account skew of the antenna, instead of being worried about one wavelength, we're now worried about things that are more than 5 feet away. And the reason for that is that when you skew the antenna, you're actually bringing in the mounting hardware of the adjacent antenna into the main beam of the antenna. And when you do that, the magnitude of the power arriving at the PIM source is significantly higher. And so therefore, anytime you add skew to the system, the hardware on the adjacent antenna has to be much, much lower PIM in order to prevent interference to the network. This has been confirmed by ConcealFab via field testing. We pioneered the development of methods to locate external PIM starting as far back as 2016. We've spent 4 years now in the field finding out and determining where are the PIM sources around antennas. And we've been able to develop an extensive portfolio of solutions to develop the most common problems that we've identified. The methodology is relatively straightforward. Step one is eliminate galvanic mismatches. And this is simple. You just make sure that every time you have a piece of metal touching another piece of metal, make sure it's the same material and same finish on both sides of the junction. The next step is, if you do have metal touching metal, which is, by the way, perfectly fine, you just have to make sure that the contact pressure between those two metal junctions is high. It needs to be a bolted connection where you're able to make sure that it can't come loose over time and temperature and vibration. If you can't achieve step one or step two, then your option is to insulate it. So if I can't maintain the same, or if I'm forced for some reason to have different metals at a junction, or if I just can't guarantee that they're going to be high contact, insulate it. Put some kind of a plastic material between the two to guarantee that they just don't make contact. And the last one is, if you can't do 1 through 3, the next thing is we'll just prevent the RF energy from getting there in the first place. And we do have RF barrier materials that are for that application that we can put between the antenna and the device that we're trying to protect and just prevent the energy from getting there in the first place. So looking at some of the solutions in ConcealFab's portfolio, the first is our replacement for hose clamps. This is a super heavy duty, it's similar to a zip tie is a good way of thinking about it, but it's incredibly high strength. It's designed using acetal, which is the name of, or Delrin is the commercial name from DuPont. The material itself is designed for over 20-year service life. These straps are designed in accordance with a Telcordia specification that's been around for more than 30 years now. And each strap is able to support more than 250 pounds of loop tensile strength at 70 degrees C or 158 degrees Fahrenheit. It actually is stronger as you go colder. But these straps provide a low PIM replacement for the stainless steel because we've just eliminated all of the metal contact completely.
Tom, can I ask a question here?
Sure.
So the first question is you were talking about the wavelength for PIM affecting different parts of the network. If you solve the PIM problem on frequencies that are lower, does that automatically capture the PIM problem that could be at the higher frequencies as well?
Yes, absolutely. So what happens is these PIM sources are receiving all this, I call it PIM soup. You receive all these different frequencies and all the potential combinations based on the transmit frequencies that are arriving are being generated. And whatever product is able to be generated by the mix of frequencies, those are what are created. But if you eliminate the nonlinearity to begin with, then all of those products are eliminated.
Okay. And then the second question I have is on these specific Delrin acetal straps that you're talking about. Is this also used as another solution for banding, or is it more geared towards tying in cables and such? Because your picture looks like it's replacing banding as well, as far as that goes.
No, this picture is actually a close-up of cable supports, and in this picture we have a 4-position bar, and so we're launching from this one support at the cable at the pole interface, 4 mounting holes for snap ends. We really don't recommend this as a true replacement for banding. It looks like plastic banding, but if you think about it, banding is typically used for structural applications where I have to support a tremendous amount of load. 250 pounds per strap is pretty darn good.
Yes.
But we derate this significantly for long-term static loads. And so realistically, I would like to see no more than 30 pounds of static load per strap, just to give it a huge factor of safety. Whereas if I have something structural that I'm trying to support, onto the tower frame or something like that, the stainless steel straps, will provide significantly higher strength than the plastic ones will.
All right, 10-4, thank you.
All right, to go along with this type of product, we've also developed replacements for the adapter brackets. So we have plastic versions of a cube-shaped three-position snap-in bracket, as well as a plastic version of the traditional trapezoid bracket. We have single-position launches for launching snap-ins, as well as the threaded rod launch. So this, once again, is eliminating PIM by just eliminating the metal-metal contacts altogether. We also have solutions that are designed for replacing those stainless steel angle adapters. We have our universal mounting system designed to launch off of the flange of steel angles that we can launch either adapters for snap-ins as well as adapters that can support threaded rods. We also have a version of 5-position cube, which is designed specifically to mount to the flat surface of an angle or pretty much any other steel flat structure at a site for supporting snap-in adapters. On the snap-in side themselves, ConcealFab has invented, and we now have a patent issued for our hybrid snap-in. And by hybrid, I mean we maintain the steel body of the snap-in for strength, but we've added a UV stable nylon insulator at all points of contact where the snap-in will either attach to the mounting structure or for snap-in to attach to snap-in. These are available from 1/2 inch to 1 5/8 in diameter, and for smaller diameter cables, we sell EPDM UV stable cushions that'll fit inside the snap-in. We also sell plastic versions of those. These are intended for smaller diameter cables ranging from 4 millimeters to 17 millimeters. And they have all the same advantages of our hybrid snap-in, meaning that there's no tools required, easy to install, easy to remove, reposition, and are inherently low PIM by design. In order to provide mounting locations for all of these snap-ins, we developed our bar solutions. We have a 13-position bar as well as a 22-position bar. They're designed from galvanized steel construction. And by design, we have high contact pressure, both where the clamps mount to the pipe and where the bars mount to the threaded rods. These are highly configurable, as you can see in the picture to the right, so that we can put mounting solutions where they're needed to support the large number of cables that are coming out of these multi-band antennas. We also invented a replacement for traditional steel strut. Steel strut by itself, there's nothing inherently wrong with the strut. The problem is that all connections to the strut tend to be sources of passive intermodulation. So what we did is we invented a solution, which now also the patent has been issued for that replaces the steel strut with a custom designed aluminum strut that has channels on opposite sides. One side is for attaching to the structure for supporting it, and the opposite side is intended for launching supports for supporting cables. We have designed a channel runner system, which is designed from a UV stable nylon that prevents all metal-to-metal contact between both the structure you're mounting to and the strut, as well as between the mounting hardware and the strut. So these are available in the material by itself for constructing frames for supporting equipment. We also sell complete mounting kits for either wall mount kits or as well as pole mount kits, for here again supporting the large number of cables that are coming out of multi-band antennas and radios. Everything in ConcealFab's portfolio that we put the PIM Shield brand on, it's not low PIM because we say it's low PIM. It's low PIM because we've tested it, and we do rigorous testing to make sure that the products that we're producing are guaranteed to provide low passive intermodulation performance. The method that we're using is in accordance with a new IEC specification that's currently still under development. When it's commercially available, it's going to be 62037-8. It's being developed by the same group of wireless professionals that are responsible for creating and maintaining the existing PIM test specifications for antennas, filters, cables, and RF connectors. This is just a new one that says we now have a method for testing things that don't have an RF connector on them by using this radiated PIM test. And as I said, the official publication date is it's on track for probably late 2021. To give you an idea of what we do when we perform this test, we take the object that we're developing, we place it in the near field of the antenna, and we radiate it with two 20-watt test tones. And while we're testing, we tap on it with a fiberglass rod. So it's a dynamic test in the near field with full 2 by 20-watt test tone power. We radiate 4 surfaces. We hit the front, the back, the left, and the right. We repeat the whole process for the opposite polarization. So we hit a slant left and a slant right polarization. And then we repeat the whole process for a different frequency. So we're testing these at both the 700 megahertz band as well as the 1900 megahertz band. And all in all, we end up doing 16 dynamic PIM tests on each product before we claim that it is a low PIM product. And this test is very effective at finding weaknesses in designs. This is an example of the data that we measured on a traditional metal snap-in. And you can see at the top that when we're tapping on a traditional metal snap-in during this test, we get very, very high peak magnitude of PIM. But if we do nothing but just replace those metal snap-ins with ConcealFab's hybrid snap-in, we're now down measuring the residual PIM of the antenna. It's kind of like tapping on a rock at this point. Nothing happens. And the objective here is if you eliminate the potential for PIM, it means now you can deploy these things in cell sites and not worry about how much energy is hitting them, because now you've eliminated the nonlinearity, which means now you've eliminated the PIM interference. So in conclusion, the RF environment at cell sites has changed significantly. The traditional methods of how we've supported cables near antennas using these stainless steel clips and hose clamps are now a problem. They're able to generate harmful interference because of the loose metal-metal contacts that are possible, as well as all these galvanic corrosion issues that we're creating. ConcealFab has a full portfolio of low PIM cable support solutions to help operators achieve maximum site performance. And we invite you to visit the Tally website to see the full portfolio of low PIM mounting solutions available from ConcealFab.
Thank you, Tom Bell from ConcealFab. Appreciate that information. It's very enlightening. The solutions you've gone over look like that it's going to be taking care of the network's needs as 5G continues to evolve. You've covered all the different spectrums that are being entered into in the 5G world. A lot of people don't realize how much more spectrum is going to be out there. And so I wanted to just say thank you for allowing us to not completely forklift out all of the existing infrastructure in there with the solutions that you've identified today.
Thank you, Tom. We appreciate you taking the time out of your day to present this to us. For sales or inquiries, please reach out to a Tally sales expert. That information is listed on the left. If you need technical or specific product support, the contact information for ConcealFab is listed on the right. If you have any questions regarding the presentation, please reach out to Tally and reference this webinar. We'll be sure to get all of your questions answered. Thank you again for attending.